Hello, welcome to this video. Today we're going to talk about induction. We're going to talk about different types of induction and what you use induction for and what the process really looks like. So, induction is used to prove some claim, whether it is the entire question or something you prove in between, in the middle. No matter what it is, that is induction. And induction looks like this. So, let's say what you need to do is to prove that some an is equal to something with n doesn't matter, something like that, where n is a natural number. Doesn't have to be an, it can also be showing some formula. And let's say 1 squared plus 2 squared plus 3 squared all the way up to plus n squared is equal to some formula. You can also use an induction for that. And then, so in regular induction, the first thing you do or the last thing you do, it doesn't matter, is the base case. The base case is the simplest case, and you need to show by hand that it works. So typically, n equals 1 is the base case, but sometimes is 0. Those are the usual base cases. Then, after you've done that, you really begin the induction process. So, what you do goes like this. Assume that it's true for n is equal to a specific number k. And then, so this is called the induction hypothesis. And then your goal is to write from that, just from that, show that it also works for n is equal to k plus 1. So that's the basic thing. Because now, think about it. So, you know that, say your base case is n equals 1. Well, you know that's true. But then you know that that implies that n is equal to 2 is also true. But then you know that that implies that n is equal to 3 is also true. And so on and so forth. So essentially, it's true for any natural number n. So that's regular induction. Strong induction is pretty similar, but it has a couple of differences. So let's talk about that. So strong induction. Strong induction, again, like I said, very similar to induction. So it's the same as regular induction. You prove some claim that you already know what you're going to prove, then you prove that claim. But in strong induction, you assume that it works. For n is equal to 1, 2, 3, and all the way on until k minus 1, and show that that implies that it's true for n is equal to k. And we'll get to the base cases in just a minute. So now, if you can show that and that the base cases are true, then you finish the proof. The base cases are a little more complicated. So, let's say this. So, actually, in strong induction, you don't use all of these assumptions. Typically, You might use more than one, but sometimes you only use one. But maybe you use the assumption that k minus 2 works, then show that means that k works, and stuff like that. Or maybe that k minus 4 and k minus 3 work, then k work. So if, say, the smallest assumption you have, that you assume is true, is n is equal to k minus 4. That with a bunch of other stuff that are bigger than k minus 4, that are after k minus 4, imply that it's true for n is equal to k. So, I'm sure you would agree with me that because k is a natural number, it cannot be 1, 2, 3, or 4, because n is a natural number. K cannot be 1, 2, 3, or 4, because then this will be negative. And so, our base cases are n is equal to 1, 2, 3, and 4. Because now, let's see what we get. So by all our assumptions, we'll have another true, being that if k is equal to 5, then you have 1 and a bunch of other stuff from 2, 3, or 4, and mean that, show that 5 works. They imply that 5 works. But then, k equaling 6, so 2 and stuff after until 5, show that it's true for 6, and then 7, and then 8, and so on. So, it's the same thing as true for any natural number n. Now that I have explained what is induction and strong induction, now let's go on to some actual examples. So, first example of regular induction. You probably already saw it and maybe various proofs of it. And this proof is going to be with induction. So, show that for any natural number n, you have 1 plus 2 plus 3 plus dot 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 all around plus n is equal to n times n plus 1 over 2. So, first of all, the base case, n is equal to 1. So, n is equal to 1. We sum all integers from 1 to 1. So, surprisingly enough, we get 1. And then, if we plug 1 into this, we get 1 times 1 plus 1 over 2. So, 1 plus 1, that's 2. They'll cancel with the 2 in the bottom, and we get 1. So, that's our base case. Check mark. Now, let's go on to the real induction. So, the induction hypothesis, we assume that it's true for n is equal to k. AKA, assume that for specific natural number k, we have 1 plus 2 plus 3 plus all the way on to k is equal to k times k plus 1 over 2. Now we're going to look at the n is equal to k plus 1 case. So when n is equal to k plus 1, our sum will be 1 plus 2 plus 3 dot 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 until k plus 1. But notice that all of the other parts of the sum are exactly this. So, So notice that the rest of these parts of the sum, except k plus 1, are all just this sum, 1 plus 2 plus 3, all the way on to plus k, which by our assumption is k times k plus 1 over 2. So we have k times k plus 1 over 2, and then I'll write k plus 1 as 2k plus 1 over 2. Now we can combine both of these because they have the same denominator 2, and take out k plus 1 to get k plus 1 times, we have k and 2. So k plus 2, and then all of that divided by 2. But now we can write this in another way. We can write this as k plus 1 times k plus 1 plus 1 over 2. And that is exactly what we needed to show. That when substituting n is equal to k plus 1, we get exactly this, because that's our formula. So that finishes off our first example of regular induction. So, for this example of strong induction, we have to show that for any natural number n, 12 divides into n to the fourth minus n squared, or that n to the fourth minus n squared is divisible by 12. Now, in strong induction, it can be a little trickier to see. What need to be your assumptions. And in this case, our assumption will be that it's true for n is equal to k minus 6. And we'll show that that implies that it's true for n is equal to k. But then, you'll note that we'll have 6 base cases to check. So we'll do that in the end of our proof. So, let's get into it. So first of all, we'll go on with our assumption. It's true for n is equal to k minus 6. Meaning that we have 12 is divisible by, 12 goes into, 12 goes into k minus 6 to the fourth minus k minus 6 squared. So let's expand this out. K minus 6, all of that to the fourth will be k to the fourth minus 24k cubed plus 216k squared minus 864k plus 1296. And then minus k minus 6 squared, so minus k squared, and plus 12k minus 36. So, now let's see where that gets us. So, we'll have the k to the fourth minus k squared in the front, because that's what we want to show that's divisible by 12. That's our goal, so it might be useful to put them in the front. Now let's look at the rest. So we have k to the fourth minus k squared. Now let's look at the k cubed term. We only have negative 24k cubed, so we have minus 24k cubed here. Then for the k squared term, the only k squared term we haven't used is 216k squared. We already used negative k squared. So we'll have 216k squared plus 216k squared. Next, for the k terms, we have negative 864k plus 12k. So that will get us at negative 852k. Then, for the constant terms, we have 1,296 minus 36. So that'll give us plus 1,260. Now, 12 divides into all of this. 12 goes into all of this. Now I want to see that 12 goes into 24, 216, 852, and 1,260. You can check in the calculator or just see it. It's not too hard. So now, because 12 divides into all of these, 12 divides into all of this. But then because 12 divides into the entire thing and all of this, that means that 12 divides into just what we have left. K to the fourth minus k squared, which is exactly what our n is equal to k case is. Meaning that we finished off our work with the assumptions. Now let's get on to the base cases. Okay, now to the base cases. Because our assumption was that k minus 6, that n is equal to k minus 6 works, and we showed that implied that n is equal to k works, we'll have 6 base cases. N is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, and n is equal to 6. So I will check those by hand in the video, but if you just trust me that it's true and you don't want to see the entire thing, you can skip to the end. So for n equals 1, if we plug it into this, we have 1 to the fourth minus 1 squared, which is 1 minus 1, which is 0, which divides into 12. It's 0 times 12. So that's a check mark. For n is equal to 2, we have 2 to the fourth minus 2 squared, which is 16 minus 4, which is 12. That obviously divides into 12. Next we have n is equal to 3, so we have 3 to the fourth minus 3 squared, so we have 81 minus 9, which is 72, which is 12 times 6, so that also divides into 12. For n is equal to 4, we have 4 to the fourth minus 4 squared, which is equal to 256 minus 16, which is equal to 240, which is equal to 12 times 20. So that also divides into 12. Then we have 5 to the fourth minus 5 squared, which is 625 minus 25, which is 600, which is 12 times 50. So that also divides into 12. And finally, we have n is equal to 6. So we have 6 to the 4th minus 6 squared, which is 1,296 minus 36, which is 1,260, which is 12 times 105, which also divides into 12. So now with all the base cases being true, that finishes off our proof. So if you like this and you want to see more content, I will be uploading more content in the future, so please subscribe. And finally, that's it.